This is a special edition of the EE111 lecture series videos. In this video, we go over topics that are not in the book, or they're not, some of them are in the book here or there, but this is miscellaneous topics that really, they don't fit well into any other part of the curriculum. So these are things that some of you probably already know them. Maybe you've gotten them in high school, maybe you got them in physics. But the book doesn't really cover them early on. It skips over some of them. It covers some of them lightly. So we kind of just toss in a few different topics, things that we want you to know, but there's not a better place to put them other than in this introductory class. So this is a grab bag of different things. Most of this stuff, won't show up on quizzes or tests. And again, a lot of it is stuff that you probably already know. Some of it will. When we get to resistor codes, that is something that you are required to know for this class, and that is covered in the textbook, but sort of the textbook kind of tosses it in sort of an odd place too, so we're going to toss it in an odd place as well. But just to set the table, this is just a bunch of assorted miscellaneous topics that we just want to make sure everybody comes into this program from a different background. Some people have lots of circuit experience, some people have very little, and we just want to make sure we get coverage of everything for everybody. So if there's something that's talked about later in the curriculum that people just assume that you would have heard of, we don't want there to be people thinking, you never covered that in any class. So this is a video that covers all those little things that might slip through the cracks. So big one, AC versus DC. This is one where usually we just kind of just start talking about it and just assume, people are familiar with AC and DC, or they've heard the band or something like that. But we don't a lot of times talk about it just sort of conceptually. Well, AC and DC, in this class, we only deal with DC circuits. So in the follow-up to this class, we do cover, it looks almost entirely at AC circuits, or circuits that have sinusoidal excitations. But we don't, in this class it's just DC, and we don't usually talk about why people use AC versus DC. And this is one of those topics that I found students have a very interesting background experience with this. People sort of kind of pedestrian encounters with pedestrian, that's not nice, but people's kind of informal encounters with summaries of why people choose AC versus DC or DC versus AC. I found it's usually very incorrect, or at least it's partially correct. It describes things in a way that aren't fundamentally true, but maybe in practice are true. So we're going to clarify that. So first of all, just to be clear, AC is alternating current, and it refers to any current, any system where the current goes positive and negative. And it's not just a sine wave like I just traced on the screen here. Anything where, if you had a current like this, that would be considered AC. If you had a current that was like this, that would technically be considered AC. Right? That would be considered AC with a DC offset. But alternating current just means the current flows in both directions. And what that means for the most part is you have to have a voltage that goes positive and negative as well. And DC is direct. So the DC is the current only flows in one direction. And again, DC could be something like this. This would also be considered DC. It's an ugly DC, but it never changes direction, so that is technically DC. Okay. There's a couple other things shown here which are neat. It's labeled as pulsating. I've never heard it described as that. That would usually be considered unregulated DC. And that's, if you have an unregulated DC power supply, that's probably what it looks like coming out of there. And then variable, again, I just pulled this image off the internet, so I don't take responsibility for all the things that are labeled here. But it does a good job of showing direct current and alternating current. So the big question is, AC, most of you probably know the wall outlets in your house are AC, power grids in your city, probably entirely AC. And a lot of people, I think there's been some movies, I haven't watched them, but I think there's been movies or Netflix shows or something about Tesla versus Edison, and they've caused people to kind of have ideas. People have weird associations now with AC and DC because of those two guys. I honestly don't know much about that. Students seem to know more about that than me. But I do know one of the takeaways when I ask students, why do people prefer AC over DC? One of the most common answers I get is students say AC travels further than DC. And that is not actually correct. That's not any sort of fundamental principle of AC versus DC. I think what people are referring to is, in the early days of power delivery systems, your options were essentially AC, which was a higher voltage AC, and DC, which was a lower voltage DC. And I think that perception of DC doesn't travel as far comes from historically when people were actually selling DC power as a distributed power technology. They were only using 100 or 120 volt DC. And it is true, if you're limited to 100 volts, and that's going to take a lot of current to transfer a lot of power. And if you transfer a lot of current, you're going to have really fat copper wires that aren't very long, or you're going to lose a lot of power. So the idea is, normally if we want to send power a long distance, the way we do that without spending an enormous amount of money is we convert it to a very high voltage. And we send lots of power as a high voltage with a relatively low current. And the reason for that is power losses are I squared R. So if we have a resistive wire, we generally want to keep those currents low to avoid those I squared R power losses. The only other way to avoid it is basically to have a low resistance in the wire, which means, paying for this really gigantic conductor if we wanted to keep the resistance low. So, for sending power long distance, which we generally call transmission, we usually do that with a very high voltage, sometimes hundreds of thousands or millions of volts, and that allows us to minimize the current and send the same amount of power. The downside of high voltage is, as seen here, is how does that song go? You got to keep them separated, right? You got to keep, if you have a 1,000,000 volt potential difference, and you let these wires get too close together, you're going to get a sparky lightning show, right? And so to avoid that breakdown, to avoid that arcing, you have to keep these conductors very far apart, and that means that when you drive down the highway, you see these giant towers with dangling conductors they're really big. They're big steel towers, and the reason they're big and they use a lot of steel and they're not cheap to build these towers is because you have to keep these conductors not only far away from each other but far away from people who could be walking nearby, and you probably don't want to get anywhere near a 1,000,000 volt conductor that's just out exposed to the air. So that's the downside of high voltage is it's dangerous and you have to keep the conductors far apart from each other. But the flip side is it allows us to relatively inexpensively send a lot of power a long distance. Although that's not a feature of AC versus DC. What's a feature of AC is AC, particularly alternating current, where the voltage and current are sinusoidal in nature. It is very easy to transform that. All you need ultimately to transform an AC system is 2 coils of wire. You have a coil of wire and you have another coil of wire that's next to it, and you produce magnetic flux, and that magnetic flux induces a current in the other wire, and you got to transform. And if you look in your neighborhood, you'll probably see on power poles in your neighborhood a little three or four wires on a power pole, and on that power pole you'll see a lot of these little cans, and typically you'll see these wires coming into the can, and then what comes out of that can goes to your house. I should have been an artist. My passion is wasted. And this can is just two just two coils of wire floating in a bucket of oil. That's it. It's literally a bucket of oil with two coils of wire in it. And that's a transformer. It's taking 7,000, 14,000 volts and dropping it down to 220 volts and putting it to your house. And that's all it takes. To transform AC, you just got to get two coils in a bucket of oil, two coils of wire in a bucket of oil. And that's not the case with DC. DC is typically much more complicated to transform. It's very expensive to transform DC. It's gotten cheaper in the semiconductor era. There's now ways to transform DC that's a little bit cheaper, but it's hard to get cheaper than two coils of wire in a bucket of oil. So it's still tough to transform DC. However, ultimately, DC is actually, other than the cost of transforming it, it's actually a better way to send power a long distance. And the reason for that is, look at this wave. If we have a signal, a current and voltage that looks like this, and ultimately, the distance that we have to keep these conductors separated from each other, that's based on the worst case scenario. So that's based on this voltage here. So our separation is based on that voltage. The size of the conductors we need is based on the maximum current flow. So all of these geometries for this infrastructure is based on this peak right here. And that peak only exists for a brief moment in time. 60 times a second or 50 times a second, depending on where you live, but it only exists for a brief moment in time. And for a similar brief moment in time, we have this region. So this region there is where we have 0 volts, that's a 0 volt crossing. We have no power transfer at that point. So 60 times a second, we have billions of dollars of infrastructure that's transmitting no power for a brief moment in time. That's not fully true. That's not actually fully true because of the way they do multi-phase power. But it's the idea is there, right? You're not fully utilizing this infrastructure when you have an AC side. So a better way, you can transfer a lot more power if you have DC that's the exact same voltage as that peak AC on the same conductor infrastructure. And there are countries that do that. It's high voltage DC transmission is something that some countries have experimented with. Although, again, there's this issue of transforming it. So this image right here, that's a high voltage DC transformer. This is a warehouse. This is like a Costco size. This is like a Costco size room with these giant semiconductor transformers with their cooling, with their tubes to keep it all cool flowing out of it. That's very expensive, very costly. It looks like it's hanging from the ceiling or so. I don't know why it's hanging from the ceiling, but it's costly infrastructure, and there's people have noticed some other issues, some practical issues. Most of these are issues just from the fact that it's not widely adopted, but in the future you might see a lot more high voltage DC implemented. Getting back to it though, I've spent a long time, I wandered on this. But there's not some fundamental principle of AC versus DC that says DC can't travel as far as AC. What people are talking about is it is expensive it's difficult and expensive to transform DC. And as a result, typically when you have DC systems, you're not able to just take a high voltage and low current and then transform it to a low voltage high current when you get to where you need it. You can't do that very easily. And so it is the ease of transforming that makes AC so popular. It's super easy to transform. And some electronics play nice with AC. If you have a heater is great with AC. You can, just AC flowing directly into a heating element. So it's 60 times a second it's wiggling. He doesn't care, it's going to stay hot. It's, filament light bulbs tend to be fine with AC, right? There's, in that 60 times a second they're dimming a little bit, but it's just a little bit. They tend to work just fine with AC. A lot of motors, you can make motors that are designed to work with AC. They work great, but some don't. And in particular, electronics tend not to play well with AC. Most digital electronics are DC only. And so that means that you have to convert. You have to convert the AC to DC in order to make those electronics that only work with DC power. And, that's why all of us have drawers full of these sort of heavy wall plug cubes. They get tangled up with other ones. So, okay. All right. That's enough of that anymore. Oh, yeah, sorry. This image right here, this beautiful, compelling image. So when we have this power, oh, boy. Sorry. When we have these conductors, the question is what metal do we use for these? Well, what's the most conductive metal out there? It's silver. The most conductive element is silver, but silver is really not popular. It's expensive and it's heavy and it corrodes easily or tarnishes easily. Copper is a popular one. So do we use copper for these power lines? No, copper is also kind of expensive. But the bigger issue is copper is dense. Copper is dense, which means if we made copper wires on these transmission towers, these towers would have to be, they'd be holding up these really heavy, they'd be holding up these strands of copper that weigh, 10 tons per strand. So typically these are made out of aluminum. So these conductors aluminum is not particularly, it's not a great conductor. It's okay, it's not great. But we like aluminum because it tends not to corrode, it forms a stable oxide on its surface, and it's lightweight. And it's not too expensive. So aluminum tends to be what these power lines are made out of. And here we have, this is actually aluminum with there's a steel core. Why do you think there's a steel core on the inside of this cable? Well, there's a steel core because you don't want to stress the aluminum. You don't want the aluminum to be your electrical conductor and also be the thing that is physically holding the wire. So the steel is there basically to support the aluminum. The steel is what takes all the stresses and strains as these things, wiggle in the wind and dangle there, separated by half a kilometer of distance between these towers or whatever. So it's aluminum, braided aluminum wrapped around a steel core for support is typically what these are made out of. Okay. Wires. In this class, we just say a wire is a perfect conductor. There's no resistance of a wire. It's ideal. That's a very bad assumption when working with high power, low resistance loads. And so when we're talking about powering things that do consume a lot of power, that do have a lot of current flow, that especially are fairly large geometrically, the wires that are used to power them are very important. They become very critical. And the sizing of wires is typically, we still tend to use AWG, which is, I think it's like the American wire gauge. It's sort of our metric for the size of wires, and it doesn't follow any sort of SI unit standard or anything. But for just casual wire use, it tends to be fine. And this is a chart here of gauge number of wire. So this would be called 4/0 gauge wire. That's a very large wire. You typically would only see that in kind of industrial settings. 3/0 gauge, 2/0. 2/0 gauge is about that's where you'll start to, you might encounter actual 2/0 gauge wire. That's a little more common. But it's big. That's still a very big wire. Your house is going to be wired with wires that are around here, maybe down to here. It's going to be sort of wiring in your house is going to be around this size. And one thing to note is the diameter of this wire. So an 8 gauge wire is going to be 128 mils. 128 mils is also called thous, is 128 thousandth of an inch. So these are very strange units. We're very far off SI units right now. And what's also important is this resistance here. So this is ohms per 1,000 feet of this material. So for 8 gauge wire, it's going to be 0.6 ohms per 1,000 feet. And you might say, well, that's pretty low. 0.6 ohms. Maybe, that's really low. That's for 1,000 feet. You're never going to use 1,000 feet. So you might say that's great. But actually, when we look into it, wire can have a big impact on the performance of devices that are connected to. We'll talk about that in the next slide. I just wanted to go over this kind of stuff. Further down it looks like I cut this chart off, but further down here is where you'll tend to get wires that you'll find in USB connectors, cables, things like that. Those tend to be between 18 and 32 gauge wires for sending signals and power in sort of bundled wire, braided wires, things like that. Oh, there's the rest of the chart. I just put it on another slide. I made these slides like an hour ago, and I already forgot what I had on here. So yeah, things that you'll buy tend to be down to this range. So like HDMI cables, where you have to have 20 to 30 conductors all bundled together in one cord. That's typically where you'll get down into these. These are pretty small wires. So these wires are diameter 8 thousandths of an inch to 5 thousandths of an inch. These are pretty fine diameter wires. They can't carry a lot of current. And they can't carry a lot of current as evidenced by, this is 420 ohms for 1,000-foot stretches. Signal zone. All right, so let's do a case study. A case study is, and this is a true story, this is Professor Lund, also known as John, in the hardware store shopping for, I have a circular saw, as we all do, and I had to, for convenience, use the circular saw in the back corner of my yard. My yard is, not to brag, but it's a decent sized yard I've got, to the point where I need longer than a 50-foot extension cord to use that circular saw at the back corner of my yard and plug it into an outlet on the house. And it's good to be king, right? It's good to have a big yard, but the flip side is you got to have a big extension cord. So I go to the hardware store and I see these 100-foot extension cords, and they have the $30 100-foot extension cord, and then they have the $90 100-foot extension cord. And I say, come on, $90 for an extension cord? No, sir. I'll take the $30 extension cord. Well, the $30 extension cord was 16 gauge wire. So this is a 100-foot extension cord. So I'm just going to, once again, my artistic abilities on display here. And we have going out to this circular saw here. Circular saw, anybody know? You've never seen a circular saw? It's like an acorn. I don't know what that is. So 100-foot. And yeah, I bought 16 gauge and went out to my yard and used this circular saw, and this thing just bit it. It just couldn't cut through anything. It was terrible. And I looked into it, and it's an 1800 watt saw, and that's powered 120 volts. And so let's look at why maybe this saw didn't perform well in the back corner of my yard with my cheap 100-foot extension cord. So that cheap extension cord was 16 gauge. So one thing to note also is when we say it's a 100-foot extension cord, there's one wire that goes out to the saw, but then there's another conductor where the current flows back. It's AC, so it's kind of going both ways. But essentially, we have the current is traveling down 100-foot stretch of wire and then back another 100-foot stretch of wire. So a 100-foot extension cord is really 200 feet of wire. And so that's something to keep in mind. Let's consider this as a circuit problem, though. And we're not going to worry about the fact that it's AC. 120 volts AC, that's AC RMS. We can treat it like DC, and it's going to, power-wise, it's going to analyze the same. You'll learn that next year. So 120 volts, and we have some resistance of the wire that's going down to my saw. Then I have some resistance for my circular saw. And then some resistance coming back. Let's call that R wire. Okay, so first of all, let's calculate the resistance of the wire. Going back, so I'm first saying we have 16 gauge wire. 16 gauge wire is 4.09 ohms per 1,000 feet. So we have 4.09 ohms per 1,000 feet. And we have we have 100 feet of that in each direction, but we'll just say 100 feet. So this is going to equal 0.409 ohms. So we have 0.409 ohms. 0.409 ohms here. And now to do this analysis, what's the resistance of my circular saw? Well, we're going to find that by sort of looking at the power and going backwards. So we know we had 120 volts, and we know we had 1,800 watts, and we know power is V squared over R. So we know that 1,800 is equal to 120 squared divided by R. Therefore, I'm just going to jump somewhere else and use space here. R is equal to 120 squared divided by 1,800. And we get 8 ohms. So my circular saw was 8 ohms of resistance. So we can put that back here. So let's look at this then. Let's look at what is so when I had this saw at the end of my driveway, at the end of my yard, and I was expecting to get 120 volts because I had a plugged in 120 volt outlet. What did I actually get? What actual voltage did I have across it? So I actually had, we can use voltage divider for this. The voltage across the 8 ohm is going to be the total voltage times 8 ohms divided by 8 plus 2 times 0.409. So my saw that was expecting 120 volts was actually getting 108 volts because I had it connected to this extension cord. And so instead of getting 1,800 watts, how much power was it getting? And again, I'm going to have to I'm just throwing stuff all over this page. I'm just throwing math everywhere. So the power was actually 108 squared divided by 8. No. Actually, sorry, let me use the actual value. 1482 watts. So rather than having 1,800 watts, I only had 1,480 watts. That's a big drop in power. So my saw that should have been getting 1,800 watts is now getting like Let's see what percentage of it that is. 80% of its power. So it's at, because of my extension cord choice, it's at 80% of its rated power. And that's, you might think that I wouldn't experience any really big setback from only being at 80% power, but I cut crazy. I'll cut through 4x6s, like pressure treated 4x6s with that saw. I'll do stupid things with it, and I'll feel that difference between 1800 watts and 1482 watts. So the question is, I went back to the hardware store and I got myself, I spared no expense, got myself a 10 gauge extension cord. So now let's see, what power would I experience that? What would my power be if I had a 10 gauge? I probably should have left myself another slide here. Okay, well, let's go back. Find 10 gauge. So 10 gauge, we're looking at 1.02. So dividing that by 10, 0.102, 0.102. My voltage equation is now going to be 2 times 0.102. Now, I'm going to have 117 volts. So 117, that's much closer to 120. And let's look at the power. My power now is 1,711 watts. So just by switching to a 10 gauge extension cord instead of a 16 gauge extension cord, I was able to gain a lot, right? That's like an extra 230 watts or so. I got an extra 230 watts out of my circular saw by going with a better extension cable. And now I don't go that crazy. 10 gauge extension cords, these are big. That's a big heavy wire. That's like a welding extension cord. So I don't tend to do that, but I'm in my shed right now, and I right before I started making the video, I noticed I had just bought a pack of extension cords from Costco. So I had, just to show you, these things are. You can't see it. Maybe you'll see it. My Zoom really doesn't want me to pitch this thing. 50-foot extension cord. You see, it's 12. It's two 50-foot extension cords. It's 12/3. It's a 12 gauge. 12 gauge extension cords. Almost as good as the 10 gauge extension cords. Not quite. They were really cheap though. It's like $30 for a two pack of 50-foot 12 gauge extension cords. That is a bargain, folks. Costco. Live for Costco. All right, so just wanted to go over that example. Wire gauge matters, especially when you're talking about high-powered devices. You're talking about devices that draw a lot of current. The voltage drop across wires can be substantial. The power change as a result of distance along a wire can also be substantial. So, okay, moving on to a new topic, switches. Switches, there's so many different types of switches. I actually find switches really neat. I find them kind of fun. They're always satisfying because you get to actually, move stuff. There's a million different types of switches. A couple things I want to mention though, poles and throws. So poles refers to the number of lines that are being switched essentially. So a single pole would sort of have one single pole being switched. Double pole has two. Yeah. So some of these are weird. They're doing this times two thing, but basically a double pole has two. So if you have if basically if a single motion of a switch moves one circuit, that's a single pole. If one motion of the switch moves two, that's going to be a double pole. If it moves three, that's going to be a triple pole. And then there's throws. Throws basically refers to how many different conductors that that switching event can switch between. So a single throw is basically just you're either connected to a wire or you're disconnected. A double throw is where you can switch between two different endpoints, essentially. So you can switch between two different. There's also a triple throw, which is the switch can sort of switch in either direction or be in the middle, and and the issue here is how many, what does one physical switch change? So does that physical switch, how many conductors is that physical switch moving, and how many conductors can it switch between is what tells you. So this whole times two nonsense, that's just where you have two of them on the same system. It's just two switches in a package. So single pole, single throw, single pole, double throw, double pole, double throw. These are important things to keep in mind. These are used a lot. Oh yeah, we had a triple throw here. So single pole, triple throw. There's lots of different styles of switches. A couple of things I want to mention also here: normally open versus normally closed. So normally open switch is a switch that in its kind of default position. Sometimes the default position is there's a spring that holds it there. Sometimes the default position is just, sometimes the switch is actually, it's getting a signal to do the switching event. Sometimes it's momentary contact. Momentary contact means when you push the switch, it only stays in that position as long as you're holding the switch down. But normally open and normally closed just refers to, is the circuit normally an open circuit or normally a closed circuit? It's fairly straightforward. So there's momentary switching. That's just it only switches while you're physically pushing it. There's bistable. That's what you're probably most familiar with, like the rocker switches on your wall. It's basically it snaps into one position and stays there. It snaps into the other position, stays there, has latching behavior. It's bistable. There's slide switches. These are if you ever use a mixer or something like that, or slide. You can or these are I don't know. A mixer's that's a different thing. I shouldn't have said that. There's rotary switches too, where it rotates into a different position of the switch. One of the biggest things that we often don't think about and neglect is switching contact. So internal to a switch, you have locations where metal touches other metal. And one thing to note is anytime you have metal touching another metal, you have a lot of important things going on. One of the biggest things that people often don't think about is when a switch switches, current doesn't flow when the two pieces of metal touch each other. Current actually flows the instant before those two things of metal touch each other, when those two things of metal get close enough to each other that you have electrons jump the gap. And the distance between those two pieces of metal have to get before that happens, it depends on the voltage that you're working with. So switches are quite often rated based on voltage. And I have a lot of students say, why does the switch matter? Why does it matter? The switch doesn't care what voltage it is. The only thing that matters for a switch is what current's flowing through it. Because if it's a tiny little thin switch, it can't handle a lot of current. And I'll say, yeah, the current does matter. The current rating of a switch matters, but the voltage rating matters too, because there's this issue of when you're initially closing or initially opening that switch, the voltage that you have is going to make a big difference. If you have a really high voltage, you're going to get a lot of arcing current, and that's going to generate a plasma. It's going to do damage to the surface if the surface isn't made of a material that can handle it. So voltage rating matters too. You'll notice in old-timey movies where somebody, has this big giant lever and they switch it and there's sparks that fly when they do the switch. That's a real thing. So there's actual switches that are switching very high voltages, very large currents, where it needs to be a big physical switch. Then they'll actually put the physical switch inside of a box because the sparks that fly off of that thing and the plasma that arcs when you do the switching is so violent and so dangerous. So that's a real thing. So voltage matters with switches, as does current rating. Three-way switching, this is something that, and again, I have this big thing where all my relatives think I'm an electrician, and I'm not. Well, I am an electrician. I'm just a very bad electrician. I do stuff, and then I break stuff, and then I call somebody who knows what they're doing. But three-way switching, you should know how three-way switching works. A lot of you saw this in physics. Some of you didn't. The basic idea behind three-way switching is you have two conductors that run between things, and either one of these conductors can carry current, or neither, either one can carry current. And so the idea is essentially, if you have a switch on this side that is a single pole double throw, and that double throw switches between these two different traveling wires, these two different wires that connect two things together that are being switched. Oops. And so basically, on one side of the switch, you can energize one of these traveling wires. And the only time that your light bulb is going to be on, or your switch is going to essentially be conducted, the only time you're going to have current flow is in the situation where both of these single pole double throw switches are connected to the same traveler. And the nice thing is that regardless of which position one of these switches is in, the other switch can always be set in a position that will allow current to flow. You just don't necessarily know which position that is until you switch it. So if any of you at your home have like a switch where to turn on the light, the switch has to be in the down position, that means one of two things. It means either it's a normal switch and the person just wired it upside down, they have the switch is physically upside down, or it's a three-way switch, and somewhere in your house there's another switch that has the other wire energized. And if it drives you nuts having to push the switch down to energize, to turn on the light, go find that other switch it in the other position, and then you'll be back to up is on and down is off. So that's three-way switching. There's not much to it. But the cost of three-way switching is you have to have two traveler wires. You have to have an extra wire going between the thing that you're switching, or between the two switches, so that the switches don't turn things on or off. They just energize a separate one of these conductors. Fuses, very important. You've probably all encountered fuses one way or another. There's all sorts of different types of fuses. We could have an entire class on fuses. We can have an entire degree on fuses. There's so much stuff to fuses if you really want to get into it. We don't really want to get into it. I just want to touch on it. The idea behind a fuse is it's a safety mechanism, which is designed to limit the maximum current that can flow through a circuit. And for the most part, we want to limit the biggest reason we want to limit the maximum current that can flow through a circuit is to prevent damage to the wiring, or damage to, the biggest concern is if you have too much current flow, your contacts are going to start to heat up to the point that they do damage to things. They melt things, they light on fire, they burn down your house, something like that. And so that tends to be the reason we have limits. We also have limits. We also have fusing to keep users safe. We have fusing to keep instrumentation safe. So even where it's not, an issue of burning down the house, there can be an issue of if something's connected improperly and you have enough current flow that's going to damage the internal electronics in something, typically where you'll have a fuse. And sometimes a fuse is basically just a device that if something breaks in the circuit because there's too much current, it's going to be the fuse. And so the fuse is something that's relatively cheap and replaceable, and it's the thing that's going to go first. There's different types there's resettable fuses. These would be like in your circuit breaker where, if you run your hair dryer and you're making a smoothie and drying your hair at the same time, and it trips the fuse, you can go in there and you can push it back. That's a latching, bistable resettable fuse. There's also non-resettable fuses, which typically these are just, you blow the fuse and it's done. So these would be Fuses like this one here, where it's a little coil of wire, where if it has too much current, the wire will literally melt, and then it'll spring apart, and it'll break the circuit forever until you replace that fuse. That would be a non-resettable fuse. And they're self-resetting. So some fuses are designed to, the fuse will blow, the fuse will open, it'll become an open circuit, and then if you resolve the issue that is causing the excess current flow, over time, the fuse will reset itself. So sometimes that means either the fuse is intelligent. I dropped my pen. Either the fuse is intelligent and it measures the current flow, and it sort of periodically measures the current, and then it says, it's resolved, it's fixed. Let's go back to conducting. Or it's a type of fuse. Some fuses basically. It's temperature that causes them to blow, and so if you have something that resets if you stop the current flow, it'll cool back down and it'll sort of reset itself that way. One thing, fuses are not all the same. So if you want a quality fuse, it can cost you an enormous amount of money. The supplies that we have in the labs at school have fuses in them that cost between $4 to $10 a piece. And they cost, it's not because there's some huge amount of current or some precision value. They cost a lot of money because they are designed to rapidly open circuit immediately when we exceed a current threshold. So those fuses are for protecting electronics, very sensitive electronics, very expensive sensitive electronics. And so we pay extra for fuses that will quickly blow. That's not the case necessarily with the fuses in your house or the fuses in your car or elsewhere. Generally with fuses, a fuse blows after a certain amount of time having exceeded a current limit. So for instance, if you have a fuse that's a 20 amp fuse, it might blow after 100 milliseconds if there's 100 amps of current. Or it might blow after 1 second if there's 30 amps of current. Right? So you see there's kind of a fuse is if you're way over current, it'll probably be a lot quicker before the fuse blows. But if you're a little bit over current, it might take a while for that fuse to trip. So it's just something else to keep in mind. I just realized I don't have my microphone plugged in. So the audio has been terrible this whole time. Hopefully, okay. Can you hear me better now? Probably. Yeah, the first half of the video wasn't my best work anyway. So now you got the good stuff. All right, so time and overcurrent determines how long it takes a fuse to blow. And again, you can pay more money to get fuses that perform better. There's holding current versus trip current. So a lot of times fuses are rated for the holding current, which is basically you can have this much current flowing through the fuse all day long and it's going to be fine and you don't have to worry about it and it's great. It's designed to handle that much current constantly forever. And the trip current, sometimes the value, that's usually the value where it says, no matter what, if your current is over this current, you will trip the fuse. It might not be instantaneously, but the fuse will trip if you're exceeding this current. And there's kind of this gray zone in the middle. There's this sort of, you can be over current, you can be above your holding current, but not quite high enough to trip. And you're just kind of pushing it a little bit. That's why sometimes you can get away with drying your hair and making a smoothie. And it should trip, but it doesn't actually trip the fuse sometimes. It kind of varies. And we'll talk about other types of fuses later on in the curriculum. There's cool ones. The lab boards that you use, you'll notice actually, I can hold these up if I can get it to show it. These lab boards, oh, that is annoying, I tell you. Right here, maybe I can get it to, right here. Yeah, right here on this edge here, right in between these switches, you can see these little fuses in here. I can't get it close enough, but these are PTC, they're positive temperature coefficient resettable fuses. These are fuses that when you have too much current, they get hot and they only cool down once you resolve the issue that's causing the excess current flow. So, and then they reset themselves. So that's interesting. So fuses designed to prevent overcurrent. The students usually ask, well, what prevents overvoltage? Well, the closest thing to a fuse that prevents overvoltage is what's called TVS protection. That's TVS is transient voltage suppressors. So the one thing to note about protecting against overvoltage is current's easy. If you can protect against overcurrent, because if the current gets too high, you just break the circuit. The problem with excess voltage, the problem with an input voltage that's too high, is you can't always just break the circuit. Even if you do break the circuit, a high voltage can sometimes find a way to wander across that break if it's very high. So typically when we talk about voltage protection, usually the types of voltage protection you see are only designed to work in transient situations. So these are sort of where you have periods of where the voltage gets too high for a short period of time. A high voltage for a long time, there's not a great way to protect against that. There are devices that protect it. There are systems that protect against that, but there's usually not a great way to do it. So most of the time when we're talking about voltage protection, we're talking about short events, protecting against a high voltage for a short period of time. These could be things like lightning strikes. These could be things like static discharge, right? When you don't ground yourself and you pick up your cell phone and you shock your cell phone. The cell phone should be protected against that sort of a thing, and they usually are, and they do so using these transient voltage suppressors. And there's a couple ways to do it. The most common way is with TVS diodes. So these are diodes that are designed to have when the forward voltage across this diode, when the reverse voltage across this diode gets high enough, it causes a massive amount of current to flow. And the thought process is if you're over voltage for a little bit of time, the thing that's causing the over voltage event probably can't provide this massive voltage and a massive current. So the idea is it probably can't provide 1 billion watts of power, although if it's a lightning strike, I don't know, maybe it can. But usually the idea is it can't provide unlimited power. And so if we're able to cause this massive surge of current through this protection circuit, that will be enough to choke that voltage down to the point where the voltage doesn't go crazy. So that's the idea behind it. There's a few different devices. I'm not going to go too much into this, but that does exist. Voltage protection does exist. Typically where you see it is in systems designed to protect against lightning strikes, static discharge, things like that. Resistors. We've talked a lot about ideal resistors. Let's talk about non-ideal resistors. Again, there's a million type of resistors. We could have a whole class on resistors. What are some of the biggest things, the biggest non-ideal effects of the resistors? The biggest one is probably power handling. A resistor cannot dissipate an unlimited amount of power. Even if it can on paper, it can't in real life. It will melt at a certain point in time. And before it melts, it'll get very hot. And when it gets very hot, typically its resistance changes. Temperature coefficient. Or, as a lot of times also with resistors, some resistors, we assume V is equal to IR. So that's a V is equal to IR is a nice, clean, straight line slope. Some resistors actually have, slightly different behavior a little bit. Some of them have nonlinearity, but temperature coefficient and power handling are two of the biggest things. So the other thing with resistors, as their temperature changes, typically their resistance changes. We wish it weren't so, but it is so. So these are two things that we always deal with. If you buy a resistor, it will have a rated power. It'll also have a rated temperature coefficient. The biggest reason for that rated power is, how does a resistor, if it's dissipating power, what's its mechanism by which it gets rid of that energy? Well, it dissipates energy through heat, and the heat normally is transferred to the air, and that's not a very efficient process. So transferring heat from a small physical dot on a board to the air, if you want to transfer a lot of power that way, that little dot that has a very small surface area is going to have to get extremely hot to transfer a lot of power, and they usually can't do that. Sometimes resistors that are mounted on a circuit board, it's a little bit easier in the sense that you can have a metal connection from the resistor to a big piece of metal on the surface of the board, and that can help you dissipate power a little bit, but power handling, always a very important consideration with actual resistors. These types of resistors that are included in your lab kit, there's, a lot of students ask, how are they made? The most common way these are made is with a carbon film that is around. So basically you have a ceramic tube that is coated with a carbon film. And this here is the carbon film. So we have a tube, and I'm just going to draw cross-sectional area here. So this tube is like this. And it's coated with this carbon film on the surface. And the way that you change the resistance is you essentially scratch a little channel in this carbon film. So you spin this resistor, and while you're spinning it, you sort of run a blade across the surface, and it scratches this line in here. And if you think about it, right, what it's making is it's making a little coil of conductor. So the slower you drag the slower you sort of drag the lathe across this resistor, the longer and skinnier this carbon film is going to be. And the longer and skinnier the carbon film is going to be, the more resistance it has. And that's how you make a resistor. It's a fairly straightforward process. If you want to make a low resistance resistor, you drag that lathe across quickly. If you want to make a high resistance resistor, you drag it across slowly. And you get more coils and a narrower conductor. And of course, they don't use an actual lathe. They don't, these things cost 1/10 of a penny a piece. So it's not like you have somebody putting this thing in a spinning machine and running a little tool across it. They're typically done with lasers, and they're typically done at extremely high speed. And usually what they do is they just do, they crank through 1 million of these resistors a minute. And after they cut them, they measure them, and a robot puts them in the proper bin after it's cut based on the precision and the measured value, and then they paint them, and we'll talk about this paint color a little bit later. But yeah, that's how they make it. It's kind of neat. I've always found it's really neat how they make resistors. The color, the bands. Most of you have already seen this because you get this in the previous class in our curriculum, but about 10 to 20% of you in this class didn't take the previous version of the previous prerequisite class to this one. And that's okay if you're transferring or if you hadn't made up your mind yet. But if you didn't, then you probably didn't see this. This is the resistor color code chart. So the stripes of color on the resistors can tell you the resistance. And it's a band code, so a different color indicates a different digit, a different decimal digit. So we have black, brown, red, orange, yellow, green, blue, violet, gray, white. And those are the digits 0 through 9. And that's all we get. We get, the colors correspond to numbers. The numbers correspond to the resistance. And the one thing to note is we just do scientific notation for these. So if you wanted to say 560 kilo ohm resistor, that would be 560 times 10 to the third. So 5603, that's what we have here. 5603. And that's pretty much all there is to it. So the number of digits matter. So the number of stripes on the, sorry, my light turned off in my shed. The number of stripes on the resistor determine the resolution of the stated resistance value. So it is possible you can have a 4-band resistor that has 2 significant figures, an exponent, and then the last stripe is going to be the precision of the resistor. And a 5-band resistor, that's going to be 3 digits of precision, a power, and then the tolerance of the resistor. And then typically a 6-band resistor is also just going to be three significant figures, a power, a tolerance, and then it's usually that last one's going to be a temperature coefficient. So that tells you how much the resistance changes per degree C. And it's listed here in parts per million. So if it were, let's see, 50 parts per million is what this one's stated at. What that means is that if this were a mega ohm resistor, its resistance is going to change 50 ohms per degree Kelvin or per degree Celsius that the temperature changes. So that's all there is to that. You do have to know this though. This is in the book. There may be a question on a test about resistor bands. It's very important that people know resistor codes, resistor band codes. There's lots of mnemonic devices also to learn these colors. If you don't know the color scheme, there's lots of mnemonic devices you can find Some of them are more lab appropriate than others, so be careful to use one that's acceptable for mixed company. So temperature coefficient. I said previously, when we look at these are typically carbon film resistors. And if we look at carbon film, it's listed here. The temperature TCR, which is temperature coefficient of resistance, simply gives it's the ratio of resistance change divided by the ratio, it's a ratio of resistance change to temperature change. So carbon is actually pretty good in the sense that amorphous carbon has a fairly small value of TCR, and it should be noted also it's negative, which means the negative temperature coefficient, also called NTC, means the resistance goes down as temperature goes up. Positive temperature coefficient means resistance goes up as temperature goes up. These, it's very interesting to see these coefficients here. These are alloys. These are popular alloys. These two alloys are popular specifically because they're designed to have a very low temperature coefficient of resistance. This is long enough as is. Crazy temperature coefficient of resistance. Superconductors. You might have heard about these in physics. A superconductor is basically just it's a material that it's got a normal temperature coefficient of resistance until it hits a certain critical temperature, at which point the resistance drops to 0, big goose egg. And that is a cool thing. When a material has no resistance, it means with no voltage, you can have an unlimited current, and that lets you play all sorts of neat games. Typically, you'll see superconductors. People tend to like the superconducting properties for the magnetic properties. That is to say, a superconductor can generate a perfect mirror image of a changing magnetic field, so it can perfectly cancel out magnetic flux, so it can cause things like, you can float magnets over them and things like that. Anyway, superconductors, typically they're used for magnet applications. But the downside of superconductors is typically this critical temperature here is very cold. The closest we've gotten as of, I think I saw a news story about this last year. The closest we've gotten to superconductor at room temperature which is sort of the holy grail. Minus 23 C is the closest we can get, and that's with like this highly pressurized material. It's like a strange material that has to be placed under these enormous, like diamond creating pressures before it achieves this high temperature superconductivity. But even that high temperature is minus 23 C. It's pretty good. It's getting better. If you can develop a superconductor that superconducts at 0 degrees C or above, you will be very rich. So if you have ideas on it, stop this video now. Stop what you're doing. Make it. Why don't you talk to old John about the best way to sell that thing before you go? We'll both retire. All right, photoresistors. Photoresistors, you may have played with these before. These are a material that its resistance changes upon exposure to light. These are usually cadmium sulfide or cadmium selenide, which is a very toxic material. It's kind of shocking that we're allowed to let people have these. It's very toxic, so don't eat those things. But it's just a material that when it absorbs light, when light strikes it, its resistance changes fairly dramatically. Usually the resistivity of the material goes down upon exposure to light. But one thing to know, if you look at these, zooming in on these things, they kind of look like this. These are often called interdigitated fingers. They're a way to get sort of effectively a very long contact area. You can get in a small space, you can get a fairly lengthy contact by doing this kind of interdigitated finger approach. These are a little bit strange because this metal, this cadmium selenide, is kind of sensitive, so you can't just, normal ways of depositing metal don't work. So usually they have to evaporate metal on the surface, so they kind of evaporate this pattern of metal on there to make these interdigitated fingers. Kind of neat. Solar cells. Solar cells are, you'll definitely see these or play with these before you leave our program. A lot of students on their own work with them. They are a semiconductor junction, so they're a diode junction, and I maybe should have talked about diodes in this video, but I don't. So they're a PN semiconductor junction that if you look at this wafer also, you know, most of you have seen these wafers. These are, the diode here is actually, the diode is actually, the width of the diode is the width of the wafer. So this is, so basically the top of this wafer, the top of this wafer is one electrode and the back of the wafer is another electrode. And it's the entire surface area of the wafer that is the active area of this diode. It's really interesting. You can see there's this aluminum, these little aluminum stripes on the top here. I'm just goobering the whole thing up. These little aluminum stripes are actually an electrode that makes contact with the top surface of this. So, but it's neat. It's a semiconductor diode, and the special thing about this semiconductor diode is when it is capable of absorbing light, and when it absorbs light, sometimes that absorbed light will generate a conductor. It'll generate an electron hole pair, so it'll generate an electron and then the absence of an electron. And there is, and you'll learn about this when you take electronics, there's this sort of built-in electric field in a semiconductor junction. And so when that electron and hole pair are created, they sort of immediately move to the outer extremities of this little built-in electric field of the junction. And once they reach the outside, they're current. They just flow. So essentially these solar cells have a current, which is a function of the amount of light striking the surface of the cell. And they can maintain a current even with a voltage across them, so they're useful for generating energy. It should be noted, though, that if you look at the current versus voltage curve for a solar cell, that if the voltage across the cell gets too high, your current will drop to zero. So that's called the open circuit voltage. And what that's saying is, I mentioned that when light strikes these cells, it produces an electron and a hole, and they move to the outsides of the junction. Well, if you apply too big of a voltage and have too strong of an electric field across this, that electric field is going to cancel out this internal built-in field. And so rather than this electron and hole making it to the outsides of the junction, they're going to go, almost made it, boom, and they're going to come back together, and then they're just going to make heat. So if you apply too big of an electric field, these conductors can't escape the junction, so they never actually contribute to current, so your current will eventually go to zero. The flip side is if you have no voltage across this diode junction, well, then there's a very high probability of this electron hole pair making it to the outside of the junction. The problem is if you have a current and no voltage, you have no power, because you know power is equal to I times V. So instead, we have there's this kind of point, and it turns out it's the point where the slope here is kind of -1 here. There's a point in this curve of maximum power. So there's a point where that has optimum power. If you look at your power curve, there's this peak power point here. That is called the peak power point. And one of the things that's common when working with photovoltaic cells, also known as solar cells, what's common is to have electronics that intelligently adjust the voltage across the solar cell to maximize this power output. So common tool is to ensure your solar cell is operating at this point. You have intelligent electronics that adjust the voltage across the panel or the cell to maximize that point. They're usually called peak power point trackers, something like that. Okay, and that's it. So that's the end of the slide. Just grab bag, throwing a bunch of stuff at you, throwing a bunch of different concepts. Some of this stuff might be interesting to you, some of it might not, some of it you might have heard about, some of it might not. We did want to mention it, though, before we move on. We wanted to throw these topics out there, let you know about them, so everybody's on the same page. Thank you, and have a great week.